Welcome back. In this video, we are going to focus on how to determine the reactionary forces. So let's pause for a second and talk about what our goal is in simple terms. Last class and the class before, we talked about design loading, which means that you should be able to determine what the applied load is on a beam. You know how to figure out the floor loading by adding the dead and the live load. You know how to find tributary area. You know how to figure out the applied load. Now, in this video, our goal is to be able to determine the reactionary forces. If this is the applied load, then these supports right here must be countering it. We got to figure out what each of these are. And also, you'll see this a lot. This is a simple free body diagram, we call this. Those that are in physics or POE, you may have done free body diagrams. It's just a simple way for us to sketch what we have. So if you see the triangle actually represents a pin connection like we did in the last video. A pin connection resists horizontal and vertical, but it does not resist moments. And this is a roller. A roller does not resist horizontal or rotational, it only resists vertical. So you'll see the triangle and the circle a lot. Also note that if there is no horizontal load, we can actually ignore them. That'll be in a lot of scenarios. All right, so we also did this last video, the fundamental principles of equilibrium. And that's saying that the sum of all forces acting on a body must equal 0. If it does not equal 0, then your structure is going to move. So we say that there are 3 ways that we could apply a force, either shear, which is perfectly up and down, perfectly vertical, or perfectly horizontal, or we can apply a torque or a moment, which is a rotational force. So all vertical forces must be equal to 0. All horizontal forces must be equal to 0, and the sum of all moments must be equal to 0. Now we're going to be using this for all our examples, all our problems. So let's just try to get a standard going. Let's just say that all vertical forces, all vectors in the up direction are positive, and all forces to the right are positive, and then all counterclockwise rotation is positive. Now, what does that mean? Let's go back to here. So we said that up is positive. When we are doing these free body diagrams, up would be positive. So the reactionary forces would be equal to a positive value, and then this would be a negative value. And then all those would be equal to 0. So let's say it would be like this force minus this force plus this force is be equal to 0, which makes sense, right? If this is 10,000 pounds, then this reactionary force plus this reactionary force must be equal to that 10,000 pounds. Okay, so moment. We talked about moments also last class. A moment is created when a force tends to rotate. It's like torque. So the magnitude of the moment is equal to the force applied multiplied by the distance. The force is applied, this distance away from where it's going to rotate, and that gives you your moment. Moment equals force multiplied by perpendicular distance. Let me give you another example of moment. Say you are a little kid again, and you are running away from your sibling. So your sister is chasing you, and then you run into your bedroom, and then you slam the door. And you're trying to keep the door closed, and she's trying to open the door. So the door, this is the door right here. This is the hinge of the door. If you are on this side, if you're looking, from an overhead view, you are trying to apply a force in this direction, and she's going to be applying a force in the other direction. So you're going to be creating a clockwise moment, and she'll be creating a counterclockwise moment. And you want to have the sum of your moment be greater in order to keep the door closed. So you have a set amount of force that you're able to apply. Where would you want to apply that force? Would you want to apply that force close to the hinge of the door, or would you want to apply that force near the end of the door? Clearly, you're going to want to put that force over here. If you put all your weight right by the hinge over here, that's not going to give you that great of a moment. So even though the same force would give you less of an ability to keep that door closed, and your sister, who might be stronger or might not be, if she applies her force way over here and you apply it over here, she might be able to open the door because her moment is greater. So that's why to get the greatest moment, it will be related to how far the distance is away from where it's going to want to rotate. So hopefully that made sense. Okay, so let's calculate reactionary forces. So again, you should know how to figure out what the applied force is right here. Now we're going to try and figure out what these reactionary forces are. Now, I think this is the first time that we've introduced kip. A kip is simply 1,000 pounds. You can think of it as a kilopound. So 10 kips is 10 kilopounds or 10,000 pounds. And also, just an FYI, a ton is 2,000 pounds. So a kip would be half of a ton. So if we apply 10 kips right in the middle of this 20-foot beam, what would be the reactionary forces from here and here? Like if me and someone were holding up a table and someone was standing right in the middle, how much would each of us be holding up? Well, I think this one should be easy, right? Each one would be 5 kips. 10 kips are applied right in the middle. Each of us are responsible for half of it. But what if it was not right in the middle? What if I'm holding up one side and another student's holding up the table on the other side, and then the student is right over here? Now we would call asymmetrically loaded. It's not symmetrical. Well, I think that you should be able to figure out that, okay, the person over here is going to be supporting more weight. The reactionary force of A should be greater than the reactionary force of B. But how much? Is this holding up 10 and this is 2? How do we figure that out? That's where we have to use the fundamental principles of equilibrium. So the fundamental principles of equilibrium state that the sum of all forces in the y direction must be equal to 0. The sum of all forces in the x must equal 0. And the sum of all moments about any point must be equal to 0. Okay, so what does that mean? Well, are there any forces in the x direction? No. I see vertical, vertical, vertical. No. So we can actually ignore f of x. And that's going to be relatively common. We typically will be doing more vertical, not lateral forces. So now we're left with the first one and the last one. So let's make an equation summarizing the forces in the y direction. We'll call this f of y of a. And I don't really care what you call it. It's just a variable. We know that there's a force going down, and we know that there are 2 reactionary forces. So we have one equation, but 2 unknowns. That should trigger your algebra brain, which is saying, nope, can't do that. So let's write it out. We'll call this positive and this negative. So the reactionary force of A plus the reactionary force of B minus 12 is equal to 0. You might want to move this 12 over, and you probably will start doing that as a shortcut later. This plus this equals that. But we can't move any further, right? We have reactionary force of A plus reactionary force of B equals 12 kips. Can't solve that. However, we can use our other fundamental principle of equilibrium, which says that the sum of moments at any point is equal to 0. What do I mean by any point? It's that you can analyze any point for this next part. So let's analyze point A. The sum of all moments at point A is equal to 0. Let's make an equation that represents that. So if we're analyzing the moments at point A, we are going to say that each of these three forces could be creating some kind of tendency for this beam to rotate about point A. So if I have this force right here, we have this force times a distance. And then we have this force times a distance. And this force times a distance. So let's see what we have. Well, what's the distance between this force and point A? Well, it's actually 0. So we have our force of A times 0. That kind of cancels out, right? Then we have this force right here times that distance, which is 20. So we have our reactionary force of B times that distance, which is 20. And that's the positive one. And then we have minus, because it's negative, since that will be a clockwise rotation, we have 12 times that distance, which is 5. So we have this cancels, F of y of B, which is our reactionary force at B, multiplied by the distance, which is 20, is equal to 60. Well, we can solve that now. So solving for that, move the 60 over, divide by 20. We know that F of y of B is equal to 3 kips. So if we have 12 kips right in the middle, we know that this right here must be 3 kips. So we just solved for one of them. So now what do? We know this and we know this. Now we're actually able to go back to this equation because we know what F of y of B is. So we go back to this equation. Now we plug in what we do know. And now we can find that F of y of A is equal to 9 kips. So here is the solution. We just figured it out. We have a beam applied or a load applied right here. We didn't know what the reactionary forces were. We know that total they should equal 12 because what gets pushed down must get pushed back up, but we didn't know how it was distributed. And now we know that this is 9 and this is 3. You also might be able in certain problems to set up a proportion saying that, okay, this is 1/4 of the total. So that will be 3/4 of the force. If that doesn't make sense to you, don't even bother. If we had class in person, I would have explained that. But for the sake of, being online, I think that it might confuse people more than it would help. Okay, that's one example. And because we are limited to 15 minutes per video, I think our next video will be doing the next 2 examples. All right, that's it for this one.